Okay, so let's look at a simple matrix multiplication algorithm in MapReduce. So before we get there, just to remind you how to think about matrix multiplication, we've got a matrix with 4 columns and 2 rows multiplied by a matrix with 2 columns and 4 rows, and the output is going to have the number of rows from the first matrix and the number of columns from the second matrix, so it's 2 by 2 in this case. Okay, and again, just to refresh your memory here, what is this result? Well, it's the first row of the first relation, the dot product with the first column of the second matrix. Right, so it's 1.1 plus 3.4 plus 4.-3 plus -2.0, and that should equal 1. Okay, and so on. So that's, let's just say row 1 and column 1 dotted together gives you this position. Row 2 and column 1 gives you this position, and so on. All right, so I'm hoping that was intensely boring. All right, so in MapReduce, how do we want to do this? Well, what we're provided here is 2 matrices representing sort of a sparse matrix format, and a sparse matrix format is going to look like this. So this is row ID, column ID, and the value. And the reason I call this a sparse matrix format is that it would be inefficient to represent a very, very large matrix this way if you had a value for every position, right? So if you think about just a multidimensional array in memory, you don't have to be explicit about the I and j coordinates. You only have to provide the values. But if many of those values in that array are missing, then in this representation, I just can ignore them altogether. I just don't put them in, right? Okay. So anytime a value of 0, just remove that tuple altogether. Okay. So we're given 2 of these sparse matrices represented as tuples, sets of tuples, and we're going to do the same trick. Matrix multiply is a binary relation, and so we need to lump them all together. And we need to tag them with the source. And then we need to apply this kind of a trick. In the map phrase, for every element ij of A, emit several things. Emit a tuple where the key equals I comma k, and I'll tell you what k is in a second, and the value is value equals A, I, j. Now, we're going to emit one key value pair of this form for every k in 1 to n, which is what I've written down here. Now, what is n? Well, n is the number of columns in B, in the right-hand matrix. Right? So A is an L by M matrix, and B is an M by N matrix. So what is this saying? This is saying for every column of B, emit a tuple with key I to k and the value at ij. Okay. So I have a diagram on the next slide that explains this. But what you're doing is you're going to replicate this value to every column in B. Okay. And then for B, you do the same kind of thing. You say the key is going to be equal to ik, and the value is equal to b jk. Okay. And you're going to emit one of these key value pairs for every I, the upside down A for all I in 1 to L. where L is the number of rows in A, right? So you have to replicate the values of B to all the corresponding rows of A, and you have to replicate the values of A to all the corresponding columns of B. Okay, so this, and then finally in the reduce phase, you can do the dot product and produce the output. So it may be hard to think about written out in notation like that. So think about this sort of diagrammatically. The first, the value 1 1 in A needs to be sent. Actually, let me back up one step. First thing to recognize is that there's going to be one reducer per output cell in this algorithm. So here we're going to have 6 reducers. And if you had really, really large matrices, which is why we're playing this game, is to imagine that we have, 10,000 by 10,000 matrices. Sorry, matrix with dimensions 10,000 by 10,000. Then this starts to make more sense. So one reducer per cell in the output matrix. Okay, and think about what data does it need in order to compute its answer. Well, it needs, for the reducer 1 1 in the output, it needs all the values from row 1 in A, and it needs all the values from B1, from the first column of B, right? All those need to be sent here. Now, fine. So maybe I'll write that real quick. We need row 1 from A, and we need column 1 from B, right? Now, let's think about this second position. Okay, so this is row 1, column 2. Well, here we need row 1 from A and column 2 from B, right? So that's fine, but the problem is we don't have data represented in terms of rows and columns in the input. We have every individual cell. So we have to figure out where should this value, A11, be sent? Well, it needs to be sent to everybody that might need it, which means it needs to be sent here because we see row 1 from A. Well, this is in row 1 from A, therefore it needs to go here. And this second position also involves row 1 from A. So this guy needs to be sent to 2 places, which is what I was trying to draw here with these colors. It gets sent, let me draw some more arrows here and see if it gets too cluttered, which I'm sure it will, but we'll try it anyway. It needs to be sent to both of those locations. So for every column of B, you need to have row this value be sent. And similarly for this guy, right? So to all the reducers that might appear in row that need the data for row 1, you need to send it to all of them. And so this is the reason I'm sort of belaboring this is that this is kind of a nice trick that MapReduce can do. Remember, you can replicate, right? You can send a single value out of the mapper to many places. And when I say send to many places, I don't mean literally sort of, write it on the wire and send a packet across the network. What I mean is attach a value to multiple keys, and then every individual key will go to a different place, to a different reducer. Okay, and through this trick, we can sort of arrange for matrix multiply to occur, and this arguably scales pretty well, right? We've done some replication, but that replication is kind of necessary, and this whole thing can sort of happen in parallel. And then finally, again, each reducer produces the sum AI times BJ. Sorry. It produces the dot product of a row of A and a column of B. Okay.